Bien, bonjour à tous. C'est un réel plaisir pour moi de vous retrouver après une petite pause que j'ai dû faire. Mais je pense que vous ne vous êtes pas ennuyés avec mon ami Thibaut David et avec toute l'équipe de Midi MINATEC aussi. Donc, je suis ravie de vous accueillir à nouveau ici. Et tout d'abord, je vais vous annoncer, donc pour l'instant, je parle en français, mais tout à l'heure, je vais basculer en anglais. Je vais vous annoncer le prochain Midi MINATEC qui sera dans 15 jours. Là, actuellement, on a un rythme de 15 jours parce qu'il y a énormément d'événements qui se tiennent ici dans l'amphi. Et du coup, on n'a pas forcément, on laisse la place aux autres événements. Alors, donc dans 15 jours, ce sera le 17 juin, d'accord ? On aura le plaisir d'accueillir Sébastien Boisseau, donc du département système du LETI, chef de laboratoire. Et lui va nous parler des objets connectés qui, actuellement, on les retrouve partout autour de nous de manière silencieuse, insidieuse parfois. Ces objets connectés, finalement, ils consomment de l'énergie. Et donc, tout le problème reste au niveau de leur autonomie énergétique. Et donc, il nous propose de venir nous parler des méthodes de récupération d'énergie, énergie qui est disponible dans l'environnement de ces objets pour les alimenter. Voilà. Donc, et puis, donc, le 1er juillet, donc le prochain, donc je vous l'annonce pas, mais le dernier Midi MINATEC de la session, enfin donc avant la trêve d'été, ça sera le 1er juillet. Donc aujourd'hui, nous avons le plaisir d'accueillir le professeur Hussein OSMAN, donc qui vient de l'Université d'Ottawa. Il nous a fait le plaisir et l'honneur d'avancer son voyage qui était prévu qu'à partir de lundi. Il vient au LETI pour 3 semaines. Et donc, je vais basculer en anglais et je vais l'accueillir. So, welcome to you here and thank you for coming before the planned date for your stay here in Grenoble.
My pleasure.
It's really a pleasure, Professor, to have you there, and the pleasure is for us to hear you about how machine can understand human emotions. So, Professor Al-Osman, the floor is yours.
Thank you so much. Thank you, everyone, for attending this talk. I know it's harder to attend in person nowadays, and for those of you attending online, thank you for attending. My name is Hussein Al-Osman. My presentation is titled, How Can a Machine Understand Human Emotions? But before I dive into my topic, let me tell you a little bit about myself. I'm an associate professor at the University of Ottawa. Ottawa is the capital of Canada. And by the way, the University of Ottawa is the largest bilingual university in the world. So that's why I know a little bit of French. If you want to ask questions at the end in French, I understand French, but I'd rather answer in English if you want to hear a coherent answer. I'm also a director for a graduate program at the University of Ottawa. It's called the Digital Transformation and Innovation Program. It's a multidisciplinary program that involves multiple faculties, and it's focused on data science and user experience. I direct a research lab there, and my research interests are in applied artificial intelligence, human-computer interaction, multimedia systems, and last but not least, affective computing, which is really what I'm going to focus on in this talk. So computers, from the most sophisticated computers to the most basic ones, kind of adopt a similar interaction pattern. The user sends a command and they send a response. But there's something missing in that interaction or that communication, and that is the emotional context. When we interact with other human beings, we are constantly modulating our understanding of the communication based on our interpretation of the emotional context. We interpret the communication in light of that emotional informational channel, but computers are completely oblivious to the emotional context. And so therefore, the field of affective computing aims to develop computers that understand human emotions and respond to human emotions so that you can have a more intelligent interaction. Now, you might wonder, why do we want computers, or even should all computers have emotional understanding capacity? Well, maybe the answer is no, we don't need all computers to understand emotions, but some maybe should understand emotions. And again, this is a little bit controversial, and we need to study the ethics of such technologies more carefully. That's why at the University of Ottawa, I collaborate with the philosopher that works in ethics. But some computers are better off if they understand emotions. For example, meet Rudy. Rudy is an assistive robot that helps individuals, and especially elderly individuals, to live an independent life. If they don't want to live in a senior residence, they can basically have a robot that assists them in some basic tasks. For instance, the robot can remind them to take their pills, or can carry light things for them, or the robot has a screen that allows them to interact remotely with their doctor, which is really quite useful for the pandemic, or other loved ones. But also, Rudy provides basic companionship. Now, obviously, you can imagine that a robot that provides basic companionship is better off having affective or emotional understanding capacities, so I can better understand the intention behind the communication, right? I can say exactly the same words in a sentence, and based on the intonation and my facial expressions, it could be interpreted as anger or surprise or sadness or even possibly happiness. And so it is not enough for Rudy or other robots or even virtual assistants in some situations to understand the communication, the semantics of the communication. The emotional context can be as important, if not even more important. Now, obviously, that's not the only application. I'm going to go over some of the applications that we developed at our research lab in the last 2 or 3 years, so that you can get a sense where effective computing technologies are used. But let's go back to the central question of this talk. How can a machine understand human emotions? Well, machines have access to a wealth of information if they have sensors on board, right? If just using a camera, we can get a video and audio, right? And that gives us the visual modality of information, where we can look at facial expression, body expression, gestures, posture, all sorts of information that are reflective of emotions. When it comes to audio, well, the computer can interpret the meaning of the communication if we are using a natural language interface, understand what we're saying, but even more importantly, understand how we're saying it. That's the intonation. How we're saying, the pitch of our voice carries a lot of cues on emotions. And so also the computer can look at that. And also, computers or machines can cheat a little bit, do something that humans cannot do, can look at physiological signals, maybe check our heart rate variability. Maybe if we have an EEG sensors that measure the electrical activity of the brain, maybe you can tap into that. So I'll get back to that later on in the presentation. But for now, let's really focus on the primary modality that is often used for emotion detection, which is the visual modality, and in particular, facial expressions. Facial expressions have been used for quite some time to recognize emotions. In fact, most of the early work either used physiological signals or facial expression to recognize emotions. And so let's try to understand, how can a computer recognize a facial expression and tie it to an emotion? In the broadest sense, a computer would need obviously an image, so it would need a camera. We use a camera, get a picture of the subject, crop out or remove all unnecessary information, such as the background or other individuals that are not the primary subject that the computer is focusing on, and just focus on the face. We take the facial image, feed it to an algorithm, and hopefully the algorithm is smart enough to recognize the emotion. Now, typically, not always, but typically, vast majority of the times nowadays, that algorithm is a machine learning algorithm. It's a special type of algorithms that is used in this area. So machine learning algorithms are simply algorithms that learn on their own how to solve a problem, right? So conventional algorithms, a developer of a conventional algorithm would have to specify, give instructions to the computer, specify the steps to solve a particular problem. With machine learning, well, we're going to let the computer learn how to solve the problem by recognizing patterns in the data. And that's the data we're going to feed to the machine learning algorithm. So we give the machine learning algorithm data and hope it learns from it. Okay, but if I give the raw image to my machine learning algorithm, I risk overwhelming it a little bit. And that's because images contain a lot of data. I mean, we don't really focus on that problem nowadays because we have a lot of memory on our phones or computers. But images have a lot of data. They're composed of pixels, lots of them. Each pixel is composed of 3 color components, the red, green, and blue channel. And so we have a lot of inputs that we are feeding to our machine learning algorithm. And we might run into a problem that is known as the curse of dimensionality. When we feed machine learning algorithm lots of inputs, we better have a lot of data to train it. And if we don't, it's just not going to train well to solve the problem. Or alternatively, instead of feeding it lots and lots and lots of data, we can extract useful information as a primary step from the image and then feed it to the machine learning algorithm. And so broadly for our facial expressions, we have 2 categories of, or 2 types of feature extraction or information extraction methods to feed to the machine learning algorithm. So I can extract features using the geometric method, and the idea of the geometric method is quite intuitive. Given that we know the anatomy of a face, we have 2 eyes, nose in the middle, mouth that goes under it, we can create a mask and try to fit that mask through mathematical optimization onto the face. We typically use an algorithm called active shape model or a variant on that algorithm. Once we fit the mask onto the face, that gives us the location of some key landmarks. We can calculate distances between these landmarks and feed that information to the machine learning algorithm. So we reduce the amount of inputs drastically. The other way of doing it is called appearance-based feature extraction. This is by far more popular than the geometric feature nowadays. And I'm going to state later on why it's way more popular. So with appearance features, we use a filter. We apply a filter to the image, and the filter is supposed to emphasize useful information while de-emphasizing useless information. So where would the useful information lie? Well, if you look at this image here of this picture, you notice that there are shadows, there are creases, there are bulges. That's useful information for recognizing facial expressions. And then if you look at the forehead area, not a lot is going on, right? You don't see subtle sudden changes in color. So maybe in that area, we don't have a lot of useful information. But in areas where we have sudden changes in colors, that's where the interesting things are happening. And so we can apply a filter that emphasizes the useful information, namely the sudden changes in colors, and de-emphasizes the boring parts where there is nothing happening or there are very slow changes in colors. Now, if we use the appearance-based feature mechanism, we need to figure out 2 things. What filter are we going to apply, and how are we going to configure it? And these are problems that are sometimes difficult to solve depending on the nature of the problem. But we'll see how we can solve that in a second. So to just summarize how this whole thing or this whole process works out, we have a machine learning algorithm that is trained, and typically we use a training process called supervised learning, meaning we give the machine learning algorithm a bunch of facial expression images along with a description of the emotion portrayed in the facial expression. We feed all that data into the machine learning algorithm, and hopefully the machine learning algorithm will find some patterns in the data during model training so that when we move to the more interesting part, or the more interesting stage, which is the inference, we can give an input to the machine learning algorithm that it has not seen before. But hopefully we've given it enough example that it kind of says, well, this image looks similar to some images I've seen, and therefore this is showing happy emotion. Okay, so I said that appearance-based feature extraction tends to be more popular nowadays. It's because it's more successful and it's easier to implement. And the reason is because nowadays there's a mechanism to go around choosing the nature of the filter and configuring it. So instead of the developer of the model or the algorithm figuring out which filter to use and how to configure it, let the machine learning algorithm learn these features automatically. So we're going to introduce the filter learning process into the machine learning process. So we combine both of them. This way, as a developer, I do not have to figure out what filter. I'm going to let the machine learning algorithm learn that filter. So we do that using deep learning or deep artificial neural networks. Artificial neural networks are networks of artificial neurons that are organized in layers. And an artificial neuron is kind of an approximation. It's a really rough approximation of a biological neuron in the brain. They really simulate how biological neurons work, but they're quite different. And so one particular architecture in artificial neural networks is called convolutional neural networks. With convolutional neural networks, we can do exactly what I mentioned. We can filter. We can learn how to filter the image so that we are able to solve the problem. So the filters that are produced through this process are exactly specialized in the task at hand. These filters run in stages or multiple layers of filtering. And so for convolutional neural network, there's a stage called feature learning, where we apply a bunch of filters that are learned on the data. And then there's a next stage called inference. And during inference, this is when we take the filtered image and try to figure out the emotion shown in the filtered image. Now, if we all displayed facial expressions that look like this all the time, then convolutional neural networks would work extremely well to detecting human emotions. Unfortunately, in the real world, facial expressions tend to be subtle or subdued. That's due to a phenomenon psychologists call display rules, meaning depending on the social context and also on your cultural background, you sometimes de-emphasize certain facial expressions. It's just done automatically. We learn it as kids. And so we don't really often display such facial expressions. And so therefore, if I use a convolutional neural network trained on such a data set, it's going to fail miserably in the real world. And it has been demonstrated that it fails miserably in the real world. This is called an acted data set, where we have a subject acting out emotions. And so such data sets, they're good for publishing papers, especially early on in the when we start working on affective computing. You can get really good results with a convolutional neural network, but they're not deployable in the real world. And so if we apply convolutional neural network in the real world, just as is, it's going to struggle a little bit. And we've done a lot of experiments on that, and it struggles a little bit. And so we need an alternative strategy. Well, if you think about how humans recognize emotions, they don't take a single snapshot in time in order to recognize an emotion. In fact, they take into account context. They see the facial expression developing and then maybe deforming back to the neutral expression. So we have a continuous stream of information. So why should we limit machine learning algorithms to a single snapshot of information? Why can't we give them also a continuous stream of information? So instead of using an image to recognize facial expressions, why not use a video? Okay, if we use a video, then we need some sort of a model that can, or a machine learning algorithm that can model sequential data. And that's where we use something called recurrent neural networks. So recurrent neural networks basically calculate their outputs. They're a type of neural networks, and they calculate their outputs based on current input and an internal hidden state. And that internal hidden state is calculated based on previous inputs. And so effectively, they're taking into account current input at time t and inputs before time t. And so now we're taking history into account. We're taking the sequential data into account. Okay, so does that mean we drop convolutional neural networks altogether and use RNN or recurrent neural networks? Well, not necessarily, because we really like the filter learning mechanisms with CNNs, but we also like the sequential modeling of RNN, so we can combine them together. And so for the CNN, or convolutional neural network, we just use the first stage, which allows us to learn the features automatically through filters, and learn the filters automatically to extract features. And in the second stage, we use the recurrent neural network for the inference in order to recognize emotions while taking history into account. And so that's what we call recurrent neural network. And the original architecture of recurrent neural networks is now known as vanilla neural network. And as it turns out, vanilla neural networks don't work very well for long sequences of data. And so we can adjust them a little bit with an alternative architecture inspired by RNN, but really modified to be able to learn better longer sequences of data, such as the LSTM architecture, or long short-term memory architecture, or another architecture called gated recurrent unit architecture. And these architectures are based on the idea of RNN, but they model longer sequences of data without problems. And also, if we want to cheat a little bit and do something that humans cannot do, we can use a bidirectional LSTM. And in that case, we're not only taking into account the past, but also the future in order to recognize emotions. Obviously, if it's a real-time system, then that cannot happen. We cannot do that if the system needs to recognize emotions in real time. But if we don't have real-time requirements, the system can cheat a little bit and do something humans cannot do. Okay, so that's the visual expression modality. What about other modalities? So let me go quickly over other modalities, for instance, audio. And I'm not going to focus on how computers recognize or understand the semantics or the meaning of speech, but how can they look at the intonation of speech? Well, there are a variety of ways to look at intonation. First of all, we need to record an audio file, obviously. That's what we call a time domain signal of the audio file. And then we can extract features from there. One way to extract features that we've been using quite effectively in the past few years is to treat audio files as images. And so we can convert the time domain signal into its spectrogram, get the spectrogram, and take that spectrogram and further convert it to what we call a MEL spectrogram. And the MEL spectrograms basically kind of mimic how humans hear auditory signals, because we don't, for instance, low frequency signals, we can differentiate between them very well. High frequency signals, we don't differentiate between them very well. And so it kind of mimics how the auditory system of human beings work. And so we end up with an image representing the MEL spectrogram. We can feed that, since it's an image and we can, learn filters to extract features, we feed it into a CNN architecture. In this case, it's a particular architecture that is well used in this area called VGG-ish. And then that CNN architecture is going to extract features, feed it to an LSTM or bidirectional LSTM, and get the emotions. And so that's for the audio modality. Now, we've been experimenting with a lot of variations on the CNN plus LSTM architecture, tweaking the CNN in some places, tweaking the LSTM in others, tweaking them together. And at some point, we reach a plateau where we cannot further improve on the performance. And that's when we started experimenting with other architectures. For instance, we got the idea to use temporal convolutional neural networks. So in that case, instead of getting the CNN to learn filters, spatial filters, to extract spatial information from the image, why not also learn filters that extract temporal information? So you would have spatial filters and temporal filters. So let me just give you an example of a system we developed at the lab a couple of years ago. So in this system, we have a video that contains audio. We take that video and obviously, detect the face and align it and feed the facial images into a CNN designed to extract features from the face. Also, for the audio, we get the MEL spectrogram and feed it into a CNN that is designed to extract features from the CNN. And that's all called spatial feature extraction. Then we put all these features together, and then we feed them into another stage of filtering and feature extraction for the time domain, or the temporal filtering. And so we apply temporal filters, for instance, across multiple frames of the video in order to extract also features temporally and eventually that data is fed into an inference stage where we recognize emotions. What about the physiological modality? I said I'm going to say a few things about the physiological modality. In fact, the work on the physiological modality is what got me interested in the first place in affective computing, and what got me started in affective computing. So computers can tap into physiological data that humans cannot do. For instance, if a subject or user is wearing some sensors like EEG sensors or the electrical activity of the brain, or ECG sensors which reflect the electrical activity of the heart, or skin conductance sensors which reflect the activity of our sweat glands, then it can process these signals, and these signals often reflect certain emotional information. But there's a problem with all these modalities, or the physiological modality in general, and that is we are asking users to wear sensors. Sometimes that's not convenient or possible, or the users are just not interested in using sensors. So that's when we started looking into other ways of extracting physiological signals without sensors. And as it turns out, that's possible. So here's how we do it. When the heart beats, it's sending oxygen-rich blood throughout the body. And that changes the color of your skin very slightly. We don't see it. We didn't evolve to see it because it doesn't help our survival, and frankly, it would be really annoying to see it. But cameras, or the optical sensors on cameras, capture that phenomenon. Even the cheapest webcams can capture that phenomenon. So we know that information is embedded into videos. It's there, it's just for us, we need to extract it. And so we've worked on various ways to extract it, and this is one of the systems that we've developed to extract physiological signals from video. First step, we obviously need to take a video and then detect the face. We try to, because the skin on the face is always exposed, so that's easy. We detect the face, and then we detect the eyes, because we know above the eyes we have the forehead, and on the forehead you have a lot of blood vessels, and so that phenomenon is more emphasized in the forehead. So we call that our region of interest. So we isolate the forehead and then average all the pixels in the forehead, so we get a single pixel, or single average of a pixel per frame, and each pixel is composed of a red, green, and blue component. And so we end up with 3 signals representing the red and green and blue channels over time. We know the information we're looking for is inside these signals. It's mixed up with a bunch of other signals, such as noise from lighting conditions, noise associated with the imperfections of the optical sensor, and all sorts of sources of noise that we don't want. So we have a source of information that we want, which is representing the heart rhythm or the heart cycles, and a bunch of sources of information we don't need. So how can we extract that source of information we need? One way to do it is use an algorithm called independent component analysis. And with independent component analysis, we assume that we have a bunch of sources of information that are all tangled up, and we try to untangle them. It works. It's not perfect, but it works. We end up untangling the heart rhythm from other sources of noise. Now, that signal is still going to be noisy, so it goes through multiple stages of filtering, and sometimes we use machine learning to further improve our filtering process. But eventually, we end up with a signal. We call it PPG signal. It's like a periodic signal that is representing the heart cycles. From that signals, we can calculate the heart rate, or more even importantly, we can calculate the heart rate variability, how the heart rate is varying over time. And since heart rate and heart activity is tied to a respiration, if we increase our breathing rate, our heart rate goes up. If we decrease our breathing rate, our heart rate goes down. And so therefore we can also extract additional information related to the breathing rate or respiration rate from that signal. So we get a wealth of physiological information that is useful for assessing emotions from the visual modality without relying on contact sensors. Okay, so we can get information about emotions from all sorts of sources of data. The facial expression, text, I didn't talk about text. Basically, it's the semantics of the speech. Voice signal, physiological signals, How do we put everything together? Well, one way to do things is to use feature-level fusion. So we extract features from every single channel of information, and we concatenate or put all these features together and feed them to a machine learning algorithm to detect emotions. So that's feature-level fusion. Or alternatively, we can use decision-level fusion. With decision-level fusion, we're going to train a machine learning algorithm for each modality separately. So train a model to detect emotions from facial expressions, train another model to detect emotions from voice signal, and so forth. And each model renders its prediction on the emotion. Then we take all these predictions on emotion, we combine them together. The simplest way to do it, probably not the best way, but the simplest way is through a voting mechanism. If 3 models are saying the person is happy, 1 is saying sad, we're gonna go with the majority, that's democracy. Or we can do something more sophisticated like using machine learning algorithm that takes all these outputs from the other machine learning algorithms that predicted emotions, combines them into a single output. So that's decision-level fusion. Or we can use some sort of a combination of both, feature-level fusion and decision-level fusion. Okay, as I mentioned, we've been working on various applications in effective computing technologies. And for the past few years, we've been focusing quite a bit on mental illness assessment using effective computing technology. So for instance, we worked a lot on bipolar disorder assessment. So from a video interview with a bipolar patient, we tried to analyze the facial expression, speech intonation, and we haven't looked at the physiological modality yet, but using this information, we try to classify their bipolar disorder state. We know that bipolar patients go from a depressive state to a manic state, and we try to make an assessment using a video interview. Also, we can apply the same technology, and in fact, we've applied the exact same models with minor modifications for depression assessment or assessing the severity of depression. We've developed applications for advertising, where advertisers were interested in seeing how engaged people are in their ads. So they wanted to monitor that, and we've worked on applications in that area. We've developed applications for mental stress monitoring, especially for employees that have especially stressful jobs, such as firefighters or police officers. And for the remote physiological signal analysis, we've used it for effective computing, but we're also using it for other purposes, such as monitoring patients in emergency waiting rooms. I don't know about here in France, but in Canada, when you go to the emergency room, you have to wait a couple of hours sometimes before you see a doctor. And typically they're not monitoring your vital signs. So with a camera, we can monitor vital signs of people waiting in an ER room. Or even there's an application to apply to senior home residents to monitor vital signs. And we're working right now on a project with surgeons to monitor vital signs post-surgery for a specific type of surgery where contact sensors is not possible to use. That's it for me. Thank you so much. Merci beaucoup. I'll be happy to take your questions.
Thank you very much,
My pleasure.
Professor Al-Osman, for this presentation. Very interesting and impressive to see how it's possible to make progress in this field. Okay, so the presentation is open for your for questions. So please, have you any questions? Yeah, please, we have a question there.
Thank you. Thank you so much for interesting presentation. I enjoyed it a lot. So yeah, it's definitely in a great interest, but can I just make maybe a naive question? So can you define first what is emotion?
What is emotion? Very good question. Excellent question.
Actually, it's just a part to continue the question.
Oh, sorry.
You need to define first, how do you see what the emotion is exactly?
Yeah, so can we define what... In fact, this is a topic, so is that the question or you want to continue?
No, I mean, if you can define in a short way, I can continue the question, but I'm not sure. What do you think?
I cannot define it in a short way. That's the short answer.
Okay, fine. So the short answer. So the question is, I see that you train the machine to recognize the emotion. That's great. Once it's recognized, you can make a response. For example, you can train machine to respond for the personality in order to heal it, for example. That's great. So you see, you have an input to the machine and output from the machine towards the personality. So what would happen if you will backloop this? A feedback you will put into the input of the machine. So you will ask machine to analyze its own emotion at some point. You see what I mean? Because our emotion, it is a response for the external emotion. For example, I'm speaking with you and I'm not aggressive, but if I would be aggressive, you will start to asking yourself why I'm doing so. So you maybe start being aggressive a little bit, maybe you reflect me and so on. And then there is auto emotion about how do I evaluate myself. This another type of emotion, what we called actually the consciousness. So can I try to have a consciousness out from the machine? You see what I mean? The feedback loop is. Thank you.
Excellent questions. Okay, so on the nature of emotions, it's actually hotly debated, and there's not a general agreement on the nature of emotions. If you're interested, there are two classical theories of emotions. One is called the James Lange theory, and the other one is called the Cannon-Bard, if I remember correctly. And they define emotions in completely different ways. And psychologists have been trying to figure that out. Honestly, the nature of emotion is a topic on its own. Now, when it comes to a machine responding to emotions and then eventually trying to assess or understand its own emotions and eventually maybe developing consciousness, that's also a kind of a philosophical question, because we still also don't understand what consciousness is and what constitutes consciousness. Now, so far with affective computing, we can never claim that if a machine understands emotions and responds even emotionally, even pretending to have emotions, cannot claim that this is consciousness. But also, it's hard to make a forceful argument that there's no consciousness there because we don't have a good definition of consciousness. We have some working definitions, but we're far from having an agreement on what the nature of consciousness is. Honestly, in my daily work, I am not really focused on the question of consciousness. In my mind, whatever the machine is doing to respond to emotions, it's faking it. It's programmed by a human being. I don't know if through repeated training, especially now that we can have what we call adversarial training, where we can have machines competing against each other to train each other to get better. I don't know if with such strategies we can get to a point where we describe that a machine is starting to develop consciousness. I honestly certainly would not like that. It's something that scares me a little bit. But I don't think we're there. The way I see it, we have machine learning programs that are simply looking at patterns in the data. And when they respond to emotions, they're just responding based on simple programs that we wrote, following instructions that we wrote. So we're quite far from there, but yeah, I don't know if that can happen in the future. I hope I answered your question.
That you can discuss together afterwards.
Absolutely.
Okay.
Yeah.
Because we need to leave some place for other questions. Okay. Thank you for understanding. So I will take a question from people that are following the presentation from on video. Thank you for this very clear and rich presentation. As far as I understood, currently, machine learning algorithms are able to extract features which we then confirm thanks to sensors. Example, measuring heart rate thanks to video will be confirmed with the heart rate sensor until the algorithm proves to be robust enough. Okay. What if the algorithms are extracting features which may be useful, but we cannot conclude on their usefulness?
Yeah, excellent question. So typically when these algorithms are extracting features, they're extracting features to solve a very particular problem. And while they're extracting features, we calculate what we call a cost function. And the lower the cost function, that means these features that they're calculating are helping us solve the ultimate problem. So these features are going to benefit the solution of the problem. So it's unlikely that we're going to get features that solve a different problem or another problem. But what's interesting about these algorithms is that once we start using these algorithms, we end up sometimes with features that we would have never thought about if we were doing it manually ourselves. So that's the advantage. These machine learning algorithms can see things in the data that we might otherwise completely miss. So if we design our own filters, they're almost never going to be as good as these filters that are automatically detecting the features and extracting them. But yeah, these features are learned to serve a particular purpose, which is to solve the problem at hand. And we're continuously monitoring to see if they are good features by checking if they are helping to solve the problem or not.
Okay, thank you for your answer. So I will ask for a question from the, yes, you have the microphone.
Hello, thank you for your presentation.
Thank you.
It was really interesting. And like you said, I think you said it before, but like we have a different way to show our emotions depending on our cultural cultural. So do you think, have you think about the way like machine will understand emotion depending on the public they will they will attend? Because if we have only one culture and at one place, it will be easy. But if we are in a country like in France, where we have a lot of cultural people, different culture, have you think about how each machine will interpret?
Absolutely, excellent question. Here's the good news. Maybe I said something a little bit misleading, and I'm going to clarify it now. So here's the good news about facial expressions. Facial expressions are universal. Even there have been studies on isolated tribes. These are tribes that haven't had a lot of contact with the outside world. And they would show them images of facial expressions and they would recognize the emotion. And they would ask them, can you do the face where you're sad? And they do the same facial expression we do. What is cultural, on the other hand, is the display rules that decide how much we're going to show of the facial expression or de-emphasize it. It's the subtlety of the facial expression. Some cultures, they show facial expressions that are a little bit more emphasized or pronounced. Some cultures, less pronounced. But the facial expression is the same. It's just how pronounced, that's decided culturally. And so that's why when we are training these algorithms, if we train them on spontaneous interviews where they see all sorts of intensities of facial expressions from the least pronounced to the most pronounced, then these cultural effects will have a lesser role to play. That does not, unfortunately, apply to all modalities. For instance, if we have a computer that is assessing speech, we have to design a different algorithm for different languages. But also within the same language, sometimes we have cultures that pronounce intonations a little bit differently. Like I've been listening to people from Paris and Grenoble ever since I came, and you guys have a certain pattern or certain intonation to emphasize the last word. I don't know if you guys notice it, but it's quite different from French speakers in Canada or Quebecers. And it's not just the accent, it's the intonation. And in that case, that can cause some problems, and you have to be careful about developing algorithms that work cross-culturally. But facial expressions, mostly universal, and they work. And there have been experiments to collect one data set from one culture, test it on another culture, and with facial expression, it works quite well. Thanks.
Thank you very much. Well, perhaps we can take a question from distance. Is it possible to publish one question that I see there? Is it time is this the time when you would take seriously the polygraph? The polygraph,
Yeah.
if I have understood, this lie detector testing machine.
Yeah. The answer is no. I don't have a lot of experience with polygraphs, but I know I've spoken to polygraph experts, and they tell me it's very easy to trick such systems. All you have to do is have some instructions on how to do it. For instance, the expert that I talked to, he told me all you have to do while you're doing the polygraph is to tense up your muscles a lot, because first they have to calibrate it. Tense up your muscles during calibration, relax afterwards, lie as much as you want. Polygraph will have no idea. So the polygraph, the way it's designed right now, it's not very effective. Does that mean that we cannot have a lie detector in the future? Maybe, maybe not. For instance, I've seen some prototypes where instead of using the typical sensors that look at muscles and heart rhythm to detect lie, some systems are using EEG, the electrical activity of the brain, and maybe that's a possible avenue for designing better lie detector systems.
Okay, thank you very much. Well, we will take a last question from the... Yes, thank you.
Je vais faire une réflexion en français.
Pas trop longue, s'il te plaît.
Oui, je pense que le système juridico-technique, que l'empathie disparaît dans le trou noir du système juridico-technique. Lors du procès de Nuremberg qui jugea les criminels nazis, un économiste réputé et un humaniste inconnu, Albert Speer, plaida que la technique coupait les relations humaines et que ça allait s'accentuer. C'était en 1946.
Yes, I don't know if you catch.
English translation, please.
Sorry?
Can you translate a little bit?
Yeah, he just pointed out that in 1946, we stated that computers will block the interaction between people.
Oh, okay.
Yeah, and so it's just, it's not a question, it's just
A comment.
a comment.
Yes, yes. Okay. Yeah, that's what I understand.
To take care with these kind of technology. Is
Yeah.
it that? Yeah.
Yeah.
Okay, so just one question for me, if you leave from me, if you let me ask for that. Now you are asking, you are trying to make the computer understand emotions. So the next step would be to, when we synthesize some voices or people speaking, we are not able today to integrate the emotion of these people in the synthesized voice. So is this work maybe will help in making possible to introduce this, to take into account emotion in the synthesis of the voices?
Yeah. So my work focuses mostly on the detection part, but yeah, I know there's a lot of activity around trying to introduce emotions into synthesized voice. It's not that good yet, but I suppose with time it's only going to get better, because the ultimate vision is obviously to have a machine that not only recognizes but also responds in an emotional way. And so both of these technologies fit together. Eventually it will fit together into computers.
Okay, so thank you very much, Professor OSMAN, for your presentation and giving us the opportunity to hear about your work. And I invite the audience to give you thanks for that.
Thank you.
Thank you very much. Okay, I will switch in French. Et donc, je vous donne donc rendez-vous dans 15 jours pour écouter Sébastien Boisseau, donc qui nous parlera de l'alimentation des objets connectés avec de l'énergie récupérée, donc dans 15 jours. Et donc, là, les sandwichs sont pour les récupérer, vous passez par les côtés et c'est à l'arrière de la salle. Et donc, je vous donne rendez-vous à dans 15 jours. À très bientôt.